Thank you, Sebastian, for organizing these tutorials. I have a similar feeling. I hope I would have attended such tutorials when I started. First of all, thank you for having me here to share some ideas on large-scale DFT simulations. As Sebastian introduced, I'm currently at the Material Science Division at Oregon National Lab. Actually, my work is I'm working on accelerating very large Dft calculations on GPUs, but today I won't be discussing my work at Argonne. Rather, I will be discussing some methods that facilitate large-scale density functional series simulations in FHI-aims and also in other codes. In particular, the ELPA eigenvalue solver and the ELSI project. So I don't think I need to say much about why we want to do DFT simulations for large systems, because we always do. Shown here are just a few examples of large material simulations. So if you want to simulate, for example, nanostructures, solids with a defect, or some interfaces between materials, you would have to create a large model which consists of hundreds of atoms or even thousands of atoms. So simulating such large systems at the DFT level is not a trivial task, as Vela already discussed. So when using local or semi-local exchange correlation functionals, the top one bottleneck that stops us from simulating very large systems is actually the solution to a eigenvalue problem, which you already seen in the previous talk. So actually, I prepared a similar plot. So I don't think I need to spend much time on this plot. So again, I'm showing you the time to solution of a PBE simulation with more than 2,000 CPU cores on a supercomputer. And of course, when we increase the number of atoms in the simulation, the time goes up, the total time goes up, but notably, the time spent on the eigenvalue problem goes up more rapidly than all the other steps. This is because the integration and electron density computation can be done in linear scaling, as explained in the previous talk. However, the solution to the eigenvalue problem conventionally is done by using a dense eigenvalue solver. The computational cost of a dense eigensolver is O(n cubed, which basically means that when we double the system size, the computational cost is increased by almost an order of magnitude, which means that for a very large system, we would like to have some better solution to the eigenvalue problem, or maybe we can bypass the solution altogether. Is there a question? No? Okay. So before discussing the algorithms to tackle the quantum eigenvalue problem, I'd like to remind you of how a supercomputer looks like today. So a supercomputer is basically a collection of smaller compute nodes connected by some very fast network. So each node has many CPU cores. So the challenge for us is how to efficiently utilize so many CPU nodes and CPU cores. And also the power of CPUs, it turns out that it's not enough for the most interesting scientific computations. So in the recent decade, people also added GPU accelerators to the supercomputers. So now on each node, in addition to many CPU cores, you also have a number of GPU accelerators, so which makes the high performance computing even more complicated. So let's look at two examples of the most powerful supercomputers in the world. So this picture shows the Cori supercomputer installed at the NERSC Center at Berkeley, California. So it is number 30 most powerful computer currently. And as you can see, it has more than 10,000 CPU nodes, which is a large number. And the performance, theoretical peak performance is 27.8 petaflop per second. So 1 petaflop per second is basically 10 to the 15th floating point operations. And another example has GPUs, which is the Summit supercomputer. It was the fastest machine on the Earth, but currently it's number 2. So it's interesting to see that it has fewer nodes than the CPU computer, Cori, but the peak performance is much higher because it has 6 NVIDIA Volta GPUs per node. So to utilize these supercomputers, what we do is we launch FHI-aims in parallel, typically using a command like MPI run or something equivalent. And we launch thousands of MPI tasks in parallel. So knowing how the supercomputers work, let's see the massively parallel eigensolver ELPA, which is, by the way, the default method to solve the Kohn-Sham eigenvalue problem in FHI-aims. So ELPA actually has 2 algorithms to solve a dense eigenvalue problem. So the first algorithm is the textbook method, which is called one-stage diagonalization method. So how it works is it first transforms this 4 matrix A, of which the eigenvalues and eigenvectors we want to compute. The algorithm transforms this matrix to a tridiagonal form, which is easier to solve. And then it uses a tridiagonal solver to solve this problem, and then converts the solutions back to the 4 matrix. This algorithm is widely used, and it's reasonably efficient, but it has a problem, which is in the first step, it has many matrix vector multiplication operations. And as Vela already mentioned, on today's computers, matrix multiplications are going to be more efficient than matrix vector multiplications. So this leads to the second algorithm in ELPA, which is a 2-stage algorithm. So instead of directly converting the 4 matrix to the tridiagonal form, it first transforms it to a banded form. And in this transformation, it can be done using mostly matrix operations, which are more efficient. And then it further transforms the banded matrix to a tridiagonal form and solves this tridiagonal matrix, and then transforms the eigenvectors back to the original problem in 2 steps. So these 2 algorithms have been available in the ELPA eigensolver library, which offers a highly efficient, highly parallel implementation. So the performance looks like this. So this plot shows the ELPA 2 solver when solving eigenvalue problems of different sizes, ranging from 8,000 by 8,000, which is sort of small, all the way up to a very large matrix, the dimension of which is 1 million by 1 million, shown here. And the x-axis of the plot shows the number of nodes used to solve this problem. So as we can see, when we increase the number of nodes used by ELPA, the time to solution goes down, which is nice. And also, for this 1 million by 1 million problem, we used more than 2,000 nodes, and it can be done in about 2 to 3 hours. So as I already said, ELPA is highly efficient for even more than 10,000 CPU cores, and it's so efficient that it has been used in more than 20 DFT software packages. But the question is, are there alternative ways to do this? What else can we do? So actually, there are many ways to bypass diagonalization, which means we do not need to explicitly solve the eigenvalue problem. So to explain what we do instead, let me first briefly remind you how we end up with a eigenvalue problem in Kohn-Sham density functional theory. So in order to solve these Kohn-Sham equations on a computer, we use some basis functions to discretize the problem. For example, in FHI-aims, we use numeric atomic orbitals as the basis functions to expand the Kohn-Sham wave functions. And after discretizing the Kohn-Sham equation, it becomes a generalized eigenvalue problem in this matrix form. Here, H is the Hamiltonian matrix, S is the overlap matrix, and the eigenvectors C basically correspond to the wave functions in this basis set expansion, and sigma corresponds to the single particle energy levels. So the key quantity in DFT is the electron density, and there are at least two ways of computing the electron density. So the first one is we sum up the occupied Kohn-Sham orbitals. So to obtain problems. And second approach is based on the so-called density matrix. So actually, the density matrix can be constructed from the solution of the eigenvalue problem. But importantly, it can also be directly constructed from the matrices H and S as a function of H and S without solving this problem explicitly. So this opens up more opportunities to bypass the diagonalization step. So actually, here I have a incomplete summary of methods that are available as a software library to either solve the eigenvalue problem or bypass it by directly computing the density matrix. So there are a number of direct eigensolvers, and also there are iterative eigensolvers, and also density matrix solvers in different flavors. So as you can see, the different algorithms scale differently. So the conventional eigensolvers scale cubically, and some density matrix solvers scales linearly, which means that its computational cost goes up linearly with respect to the system size. So one problem is that having so many different algorithms available, how do we know which one we should be using for our given problem? Actually, there was no good way to even do a systematic comparison of the performance of all of these different algorithms. What we would like to have is we want to get this algorithm into a unified framework such that we can research their computational cost and their accuracy systematically. So this actually motivated us to develop a software infrastructure called ELSI, which is basically a unified interface to a number of existing eigensolver libraries and density matrix solver libraries. So what ELSI offers is a code, an electronic structure code like FHI-aims. If it's interfaced with the ELSI interface, then ELSI takes care of the conversion of the matrix format and so on, so that the DFT code automatically has access to all the different eigensolvers and density matrix solvers supported by ELSI. And the conversion of the matrix format is done in parallel. And also another challenge for end users is each of the solvers has a number of parameters to tune. So based on a number of benchmarks, which I'll be showing in a minute, we basically defined reasonable default parameters. So if you don't want to play with the parameters, you can rely on the default values. And the interface can also, based on previous benchmarks, it can recommend which solver to use for your given problem. So this ELSI interface software is already being used in, as far as I know, 4 electronic structure codes, including FHI-aims, of course, and also other DFT codes using pseudopotentials. And actually also it's used in density functional tight banding theory. So next we will see how the different solvers perform differently on the in these different DFT codes. So the first solver I want to discuss is called PAXI, which stands for pole expansion and selected inversion. So it is a density matrix solver, which means that it computes the density matrix P as a function of the Hamiltonian H and the overlap matrix S. So in other words, it doesn't compute the eigenvalues or eigenvectors of the Hamiltonian matrix. So what's special about PAXI is there is a inversion of this H minus S project, and typically a matrix inversion also scales cubically, but here PAXI only computes the elements that are useful to, which would contribute to the electron density. Which means that only selected elements of this object is computed. By doing this, the computational cost is reduced from cubic scaling to linear scaling for 1D system, and n to 1.5 for 2D system, and O(n) squared for 3D system, which is a big improvement over dense eigenvalue solvers. And another nice feature about PAXI is the method is generally applicable to both systems with a bandgap and without a bandgap. So most traditional density matrix algorithms actually have difficulties when treating metallic systems, but PAXI doesn't have this problem. And in terms of high performance computing, actually, this is a expansion in terms of poles, and the poles are actually independent from each other. So each term in this summation can be computed fully in parallel. So you have a number of terms which are nicely distributed across the MPI tasks or computer nodes, which leads to a very efficient parallel implementation. So another feature of PAXI is instead of dense linear algebra, it actually leverages sparse linear algebra. Actually, for large systems, the matrices in DFT tend to be sparse, which is because the basis functions are localized. So if for large systems, two basis functions far from one another, they do not overlap. So the corresponding matrix element would be 0. So there are two ways to represent a matrix in a computer. So the dense storage is straightforward. It's just, it's basically the same mathematical representation. So the memory access in this dense storage is trivial because you have continuous access to the matrix elements. And there are highly optimized linear algebra routines, for example, the BLAS routines for both CPUs and GPUs. So for example, if you multiply two dense matrices together on a GPU, you get very good performance. But the problem of this, especially for large system, is the memory requirement goes up very rapidly. So which means that for large system, you run into a memory problem, even if you distribute the matrix. So another storage strategy is to only store the non-zero elements marked by blue squares here. So we drop all the zeros, which means that the memory consumption is reduced because we don't store the meaningless zeros in the matrix. And we also lower the operation count because when we multiply two dense matrices, the zeros are also multiplied together. But here we can only operate on the non-zero values. But what's tricky about this format is the memory access becomes difficult because you need to rely on the row and column indices to know where this element is, and also in terms of basic linear algebra operations, you may need to write your own customized routines because the existing optimized routines are more targeting dense matrices. So nevertheless, PAXI uses the sparse format to reduce memory and to lower the operation count. And the benefit is shown here. So this is a benchmark of a quasi 1D germanium nanotube. So again, on the x-axis, we increase the number of atoms in the simulation system. So we compare the performance of the ELPA eigensolver and the PAXI density matrix solver. So apparently, PAXI outperforms ELPA, and especially for large systems. This is because, as I already mentioned, PAXI scales linearly for 1D systems. So you can see the slope for ELPA is bigger than that of PAXI. So for a 2D system, PAXI is also very competitive because of its lower scaling. So here for this particular system, for small number of atoms, ELPA is faster than PAXI, but as we go to larger systems, PAXI is actually faster than ELPA by a factor of 2 to 3. And for 3D systems, the story is different because now ELPA is actually faster than PAXI because for such 3D systems, the matrices are not as sparse as in lower dimensional systems, which makes PAXI not as efficient as for low dimensional systems. So another factor we need to consider is how many CPU cores, MPI tasks we use. So on this page, again, ELPA, the performance of ELPA and PAXI are compared as a function of the number of CPU cores. So ELPA scales quite nicely. It outperforms PAXI for this 3D graphite system. But as we further increase the number of CPU cores, we see ELPA scales only up to 20,000 CPU cores, which is very good, but PAXI is even better. It shows a almost ideal scaling up to, in this case, 60,000 CPU cores. So if you have a very big computer and you have thousands of CPU cores, maybe you should consider PAXI, which is more parallel efficient than ELPA in this extreme cases. So another density matrix algorithm which could work for a very large system is the so-called density matrix purification algorithm. It is a established method in the community. It was developed like more than 20 years ago, but it's not very widely used until recently. So actually, the idea is similar to PAXI. Instead of solving the eigenvalue problem, we express the density matrix as a function of the Hamiltonian matrix. So here, instead of a expansion, it uses a iterative method to purify the density matrix until it satisfies the known conditions of the exact density matrix. So the purification function is typically a matrix polynomial. So one of the most widely used example is the second order reciting purification formula, which is the formula is very simple like this. So as you can see, it involves basically nothing but matrix multiplications because it needs to compute the square of this trial density matrix. And it can reach linear scaling by using sparse matrix multiplication kernels in the NT-poly library. So actually, in a recent paper, Honghui Shang and co-authors applied this NT-poly density matrix, sparse matrix technique to density matrix perturbation theory, and they can reach linear scaling. So if you're interested, you can refer to this reference. So I'm not going to show you how NT-poly performs in FHI-aims, but here is an example in a density functional tact binding calculation with the DFTV plus code. So again, we compare the performance of the different solvers. So in addition to PAXI and ELPA, we now have NT-poly, and you can see for a box of water molecules with more than 4,100 atoms, NT-poly is much faster than the other two solvers. And for this silicon supercell, we see a crossover point beyond which NT-poly is able to outperform ELPA. And actually, the density matrix purification method reaches the same accuracy as the other eigensolver and PAXI solver. So in this particular example, the band structure energies, which is basically the sum of the eigenvalues, agree across the three solvers within 10 to minus 5 electron volt per atom, which is quite nice. So now let's move on to the next topic, which is how to use GPUs in DFT calculations. So as we all know, GPUs are becoming very popular in today's high performance computing and supercomputing. So a GPU compared to a CPU, it has more cores, although each core is not as powerful as a CPU core. The combined they are very suited for highly parallel tasks like matrix operations found in DFT simulations. And also the power consumption is more competitive than traditional CPUs, which means that we can pack more GPUs together without worrying about power. So actually, as of today, more than half of the top 10 supercomputers already they are equipped with GPU accelerators. And I think there will be more in the near future because it has been announced that GPUs will power the first X-scale supercomputers in the United States, which means that in the near future, we can do 10 to the 18th floating point operations per second thanks to GPUs. So GPU acceleration in FHI-aims, which Vila also covered already in his talk, we can do Hamiltonian integration, electron density, forces, and stress tensor on NVIDIA GPUs. And I will be discussing GPU accelerated ELPA eigensolver. So first, let me briefly introduce how a GPU works in a programming point of view. So first of all, we need to keep in mind that CPU and GPU have separate memory space. So in order for a GPU to access data on the CPU, the data must be transferred from CPU to the GPU. So a typical GPU accelerated program may look like this. So the input is initialized on the CPU side, and then the data is transferred to the GPU, which performs some computation on the data. And then maybe the CPU has to do something, so the data has to be copied back to the CPU and then copied back again to the GPU and so on. So to reduce the communication between CPU and GPU is very important to achieve high efficiency for GPUs. So for example, we can move this computation from the CPU to the GPU. By doing this, we avoid two copies of the between the CPUs and GPUs, and we can save a lot of time because computation on the GPU is much faster than the communication between CPU and GPU. And also, GPUs are highly parallel. They have thousands of cores. So for a small system, we'd better not use GPUs. So it's better to stimulate big systems with GPUs, which means we feed the GPU with big data to keep GPUs saturated. And apparently, when the GPUs are doing some computations, the CPUs can be idling or they can be doing something different, like they can do some other tasks suited for CPUs. So by overlapping CPU and GPU activities, we can further reduce the total computational cost. So those strategies have been utilized to develop a GPU accelerated ELPA two-stage eigensolver, which is the first distributed memory and GPU accelerated eigensolver. So there's some noise. Hello? Is it just me or there are some background noises somewhere?
I think someone might need to be muted, right?
Okay. So I've shown you this picture before. It shows how the two-stage ELPA solver works. So the solution of a eigenvalue problem is carried out in 5 stages, and four of them have been ported to GPUs. The second stage is quite fast, so currently it is running on CPUs. So how this is done on GPUs is basically we move the dense linear algebra operations to the GPUs by using the cuBLAS library. For example, we can offload the matrix multiplications to GPUs. GPUs are quite good at doing such kind of operations. And for the fourth stage, we wrote some CUDA kernels to do householder transformations of the eigenvectors in parallel. And as already mentioned, we tried to minimize the communication between CPUs and GPUs. So I'd like to highlight a very large eigenvalue problem solved by the GPU version of ELPA, which is done by this guy in Warsaw University of Technology. So in his study, he solved a complex valued matrix, the dimension of which is over 1.7 million by 1.7 million, and all the eigenvalues and eigenvectors were solved using 4,000 summit nodes, which means 24,000 NVIDIA GPUs. This is, to my knowledge, the largest eigenvalue problem solved as of today. So now let's see how much speed up we can obtain by solving the eigenvalue problem on the GPU. So this plot compares the reference CPU version of ELPA 2 on the Summit computer with the GPU version of the one-stage ELPA solver and the GPU version of the two-stage ELPA solver. So we can see that by using GPUs, both ELPA 1 and ELPA 2 outperform the CPU-only version. And the advantage of the two-stage algorithm is that it shows a better scaling, which means that when we increase the number of nodes, ELPA 2 is going to be more efficient. And on one node for a 40K by 40K real matrix, we get a speed up of almost 15-fold. And the speed up becomes smaller when we increase the number of nodes, which is because there is fewer work per GPU card and more communications going around between the large number of GPUs. So this is the behavior to be expected for ELPA and also for FHI-aims as a whole. And we can observe a larger speed up factor if we solve a larger problem. Here, instead of a real matrix, if we solve a complex matrix, we can see the speed up becomes larger, which is because the workload is bigger to better keep the GPUs busy. And similarly, if we do a 100K by 100K matrix, we got even bigger speed up factors because of the larger workload. And here, the CPU-only version just cannot solve the problem unless you use a big number of nodes. But the GPU version is apparently more efficient. So this speed up can also be observed in FHI-aims. So this is an example of a PBE simulation. So this plot compares the performance of the ELPA solver on Summit 2 nodes only, and on the Cori supercomputer 40 CPU only nodes. So basically, the performance on 2 Summit nodes more or less matches the performance on 40 CPU nodes, and the accuracy is basically the same. So in other words, we are not sacrificing accuracy. And similarly, by using 4 Summit nodes, we got more or less the same performance as 80 Cori Haswell CPU nodes. So this problem, this is a series of supercells of this CBTS material, and the largest one contains 3,000 heavy atoms, and the eigensolver finishes in like 200 seconds only. So next, I'm going to briefly introduce the frozen core approximation in FHI-aims, which is going to speed up simulations for heavy elements in FHI-aims. So the idea is quite simple, just similar to what the pseudopotential community is doing. So basically, we know when atoms get together and form molecules or solids, only the valence electrons change. So the core electrons barely change. So which means that it's reasonable to keep the core part of the problem frozen. So we have added a frozen core approximation to the ELSI interface, which can be used automatically by specifying some parameters. So the idea is the matrices in this Concham eigenvalue problem are partitioned into 4 blocks, including a core block and a valence block. And we keep the core block frozen, which means that we do not compute the eigenvalues and eigenvectors of this block. So instead, we use the atomic eigenvalues, atomic solutions to approximate the solutions of the frozen core region. And we use a transformation to transform the matrix to a valence-only Hamiltonian, which is the frozen core Hamiltonian. It looks like this. And then we only diagonalize the frozen core Hamiltonian. The dimension of this frozen core Hamiltonian is smaller than the full matrix, which means that we can save time, and hopefully we get the same accuracy, which is true. Shown here is a accuracy, a benchmark of the accuracy of the frozen core approach, which is carried out using a benchmark set consisting of more than 100 compound materials. So we show both light default settings and tight default settings in FHI-aims with different cutoff energies. So the cutoff energy here basically means that for orbitals whose energy is below -600 eV, the orbitals are frozen. And here the cutoff is -200 eV. So we can see for all the 103 compound materials, the error in the total energy is very small. Basically, there are two algorithms. For the better algorithm, which is what we call FC99 plus C plus V, the average error is around 10 to -5, 10 to -6 eV per atom for both light and tight settings. And even if we use a high cutoff energy like -200 eV, the accuracy is quite nice. And this is further confirmed by Dr. Yi Yao by running the delta test, which tests the band structures computed by Dft code. So it turns out that using the frozen core approximation is also very accurate for band structure calculations across a broad range of different materials. And how much time we can save. So this is just an example of this cesium lead bromide material. So this is shown here is a small cell. Actually, in the benchmark calculations, I created a 4x4x4 supercell of this material, which contains 2,500 atoms and almost 100,000 basis functions. So by setting the cutoff energy to -200, I can keep 28,000 basis functions frozen, so which reduces the size of the Korn-Sham eigenvalue problem by like 35%. And this figure shows the speed up observed on the Cori supercomputer using different number of nodes. First of all, again, the accuracy is not sacrificed by using the frozen core approach in the eigensolver. We recover the same accuracy for not only the total energies, but also the forces needed for relaxation and MD and so on. And the speed up is about twofold, which is quite good because basically you get this speed up for free without any loss of accuracy. So actually, that already brings me to my summary slide. So I've showed you some approaches to facilitate large Korn-Sham density functional series simulations with FHI-aims. So it's powered by the linear scaling integration scheme, as Vela discussed in his talk. But for large systems, the more important problem is the solution to the eigenvalue problem. And actually, the ELSI interface offers you many different choices to solve this problem. In particular, we highlight the ELPA 2 eigensolver, which is highly efficient for systems with up to some thousands of atoms. And if you are going to simulate a sparse low-dimensional systems like nanotubes or graphene or something like that, density matrix solvers, which make use of sparse linear algebra, might be a better choice. And if you have access to GPU accelerators, FHI-aims is able to utilize the power of GPUs. And also, we have frozen core approximation useful, which is very useful for, especially for heavy elements. And I also want to briefly say some words about some other approaches which are promising, which has promising progress in the community. So the first one is based on machine learning and deep learning, of course. Basically, people use deep learning to learn the interatomic potentials, which can speed up the calculation by many orders of magnitude. And also another popular trend is to reduce the precision in the calculation. So by default, most of the DFT codes use double precision for the computations. But in recent years, people have figured out that for some operations, we can reduce from double precision to single precision or even half precision. Actually, for some operations, reducing the precision actually doesn't affect the numerical results at all, which doesn't mean that a single precision can be used in every operation in the code, but it can be used somewhere. And GPUs in particular, they are very efficient for single and half precision. So this is another opportunity to further speed things up. And another trend is that instead of using one GPU or like 10 GPUs, I mean, we want to use tens of thousands of GPUs, which means the biggest supercomputers today. So actually, by combining this approach, these three approaches together, people have reported ab initio simulations of more than 100 million atoms. So here are some interesting references. So actually, I'm not trying to say that these approaches have no problems, but I think they are exciting and promising directions for future research. Because my time is limited, I didn't go into all the details about the large-scale calculations and GPUs, but here I list the key references, so you can check them out. And those are the funding agencies and supercomputing centers where the benchmarks of this work have been done. Thank you for your attention and questions.
Thank you, Victor, for this very great talk. And now I leave the stage for questions. So there's one in the chat by Ramon. Ramon, do you like to ask the question yourself?
Yes, I can ask myself.
Sorry, your volume is quite low. I cannot hear you.
What about right now?
It's much better.
Good.
Yeah, I just wanted to ask you if you could explain a little bit in more detail the motivation of using this two-stage tree diagonalization algorithm, in particular, why to build this banded matrix.
Sure.
Thanks.
Sorry. Let me go back to this. So the short answer is to avoid matrix vector multiplications. So from here to here, what we do is we basically transform the matrix column by column. So we first transform the first column of the full matrix A to the target tridiagonal form, and then we transform the second column and so on. So because the matrix is Hermitian, after we modify the first column, we must apply the transformation also to the first row, and which means that the second column cannot start before the first column finishes. So by introducing a banded matrix, so when we transform the first column to the banded matrix, we are only modifying this part of the first row without affecting the second, third, fourth columns of the matrix. So which means that these columns can be bundled together to form a matrix operation, which is more efficient than matrix vector operation. This is a short answer, and to get more details, you need to check out the references here. But it turns out that this two-stage diagonalization is more efficient thanks to more matrix operations, and it's more scalable. It can use more MPI tasks, more CPU cores, thanks to more details of this algorithm. I don't know if this answers your question.
Yes, yes. Thanks. Thanks a lot.
Sure. Actually, let me see some more words. So from the banded matrix to the tridiagonal matrix, the transformation is similar to this. Basically, we transform this banded matrix column by column, but here the operations are done on very short vectors. So this is faster than doing the same operation on very large vectors. So that's why I mentioned in the GPU part that the transformation from banded to tridiagonal is very fast. But the price to pay is that for the corresponding back transformation, you have two steps, which means that the one-stage algorithm is actually sometimes faster when we compute all the eigenvectors, because when we compute all the eigenvectors, the two-stage algorithm needs to back transform all the eigenvectors in two steps. But in a typical DFT simulation, maybe we only compute all the occupied states plus a few empty states, which means maybe, let's see, half of the eigenvectors, which makes the back transformation of the two-stage algorithm less expensive.
Are there more questions? Villa, you raised your hand.
Yes, so I have one question, Victor. In the frozen core approximation, it's new to me. When the cutoff energy, how do you know which objects to cut by the cutoff energy before you solve the eigenvalue problem?
We use the solution of the atomic problem. Yeah.
So basically, you assume that the H matrix, the core block, is the atomic solution.
Yes, yes. And I mean, I didn't go into details. We have some small corrections to make it more accurate. So we take the atomic solution and apply a small correction, which is able to recover the solution of the full matrix.
Okay, yeah, thanks.
I did want to add, because I mean, this is relatively new, but in the current mainline version of the code, so the development repository, which will become the next stable version, and according to Yi Yao's tests, this is essentially stable and accurate, even if you freeze states below 50 electron volts. I thought that 100 electron volts would be nice, but it seems that even 50 is there. And so at the eigensolver stage, if your eigenvalues are limited, that's actually, and if you're doing production DFT type things, then this is actually a fairly useful speed up. You could, if you want, you can always revert to all electron later if you wish in the code.
No, of course, for historical reasons, I have to ask that. For the corrections, can you now use different atomic solver, for instance, with the different relativity treatment? Are the core states any more dependent on anything else but representing certain subspace?
You'd have to program it. That's not,
Yeah, but in
not
theory,
currently programmed.
Okay. I was just curious because historically there has been some Fockenels, you know, it's a long story, but finally it apparently works.
Yeah, I forgot to mention, I took Paula's code and modified it into the current version.
Okay, even better, thanks.
Yeah, so actually I have a question myself. So as Vela mentioned, this GPU working after FHI-aims is currently limited to NVIDIA GPUs. So in my current work, we are moving to like OpenACC and OpenMP in preparation for future AMD and Intel GPUs. I don't know what's the plan in FHI-aims.
I think the current plan, to my knowledge, is to remain with MPI3 for shared memory. So MPI3 seems to be a good paradigm, and support the native languages, unless somebody comes and contributes a different plan, right? So OpenACC, for instance, is heavily and perhaps for good reasons pushed by NVIDIA. And that is nice, but it's not compatible with Intel and AMD, right? Which is the downside. But if OpenACC happens to work well for NVIDIA,
there
sure.
are tools to automatically convert OpenACC to OpenMP. It does maybe 80 to 90% of the job, and there are a few pragmas that the tool doesn't understand, and then you need to manually update those. But for device offloading, OpenACC and OpenMP are quite similar in our experience. And it's very easy to use. I think it improved a lot. It's much easier to program than like 3 to 4 years ago.
Yeah, it's a performance question, right? That was what was the original question.
Yeah, so in our case, OpenACC is quite close to CUDA in most cases, but for some kernels, it's hard to reach the same performance. So for those highly specialized kernels, you would need to use CUDA, or in the Intel case, maybe DPC++. But for most trivial loops, it's very efficient, I would say. I mean, just based on my own work. Yeah, if no more questions, thank you, the organizers, again for letting me talk today. And I'll also be here tomorrow. So if you have questions, you can reach me offline or tomorrow in the hands-on tutorials.
Yeah, thank you so much, Victor. And I also like to thank Wille again. And if I understand correctly, Wille, you will be tomorrow at the tutorial too for a few minutes at the beginning.
I can probably make 1 hour from the beginning.
Perfect. So if you have any questions or dreams overnight, maybe you can also ask tomorrow Wille and Victor again. And otherwise, yeah, many thanks again for this really nice talks. I will stop the recording.